Good morning. What we're going to work on today is the epicenter of an earthquake lab activity. And I know you guys probably don't have everything you need for this activity at home, so just follow along with me and fill in the things that you can fill in. When we get to the part where we're drawing circles, just sketch them in as best you can. So you should have your Find the Epicenter Earthquake Student Activity Lab. And I hope I remembered to send these little ruler pages home for you. If I didn't, or you can't find yours, like I said, just follow along. I've got mine here for us to use. I also have a scratch piece of paper. Again, this is kind of just for me to keep track of some work that we're going to write down. If you don't have a scratch piece of paper, that's okay. So really, all you guys need is your lab paper here. All right, let's go through the directions. On October 17, 1989, as the Oakland Athletics and San Francisco Giants were warming up in Candlestick Park for the third game of the World Series, a major earthquake struck the area. Seismologists, individuals who study earthquakes, determined the origin of the quake was located near Loma Prieta Peak in the Santa Cruz Mountains. Discover how the starting point of an earthquake is determined. Background. The rocky plates that make up the Earth's crust are in constant motion. The interactions of these plates create faults or cracks that offset the Earth's crust. Continuous movement of the plates builds up pressure until the rocks along a fault shift or break, releasing energy that causes an earthquake. This is similar to what happens when you snap your fingers. The force between your fingers increases until the fingers suddenly slide past each other. The snap is caused by the release of energy in the form of sound waves. Energy from an earthquake is transmitted through the earth in the form of vibrations known as seismic waves, from the Greek word seismos, to shake or quake. Two types of seismic waves travel outward from the focus, the origin within the earth, of an earthquake. The primary wave, or P wave, is a compression wave that forces rock to compress and expand in the same direction the wave travels. See Figure 1. P waves travel through the earth at an average speed of about 5 kilometers per second. Secondary waves travel at a slower rate, averaging about 3 kilometers per second. Secondary, or S waves, are the transverse waves in which the vibrations displace matter perpendicular to the direction the wave is moving. See Figure 2. Primary and secondary waves are called body waves since they travel through the body of the earth. Once these vibrations reach the Earth's surface, the energy is transmitted as surface waves. These waves travel more slowly than body waves and cause the most destruction as the Earth moves up and down, like an ocean wave, and also from side to side. The epicenter of an earthquake is the point on Earth's surface directly above the focus. See Figure 3. Knowing how seismic waves travel enables seismologists to determine the location of the epicenter of an earthquake. Vibrations from seismic waves are detected by instruments called seismographs and recorded on seismograms all over the world. The faster P waves are detected first, followed by the S waves. See Figure 4. The greater the delay between the arrival times of the two waves, the farther the waves have traveled. Think of two runners on a track, where one is running consistently faster than the other. The distance between the two runners will gradually increase as the race continues. So on the side here, you can see all those pictures that it was referring to. This top one is the P wave. Remember when we did that with the slinky in the classroom, and we gathered up the coils at one end and let them go. This one is the S wave, where we waved the slinky side to side. Here's the picture of the epicenter. Remember, the epicenter is on the surface directly above the focus, which is underground. Waves go out in all directions from there. And then this is your seismogram. So you can see on the seismogram where the P wave arrived, where the S wave arrived, and how we can figure out how much time passed in between those two things. Once the delay time between the P wave and the S wave is known, the distance the waves have traveled can be determined using a graph. The direction from which the waves traveled, however, is unknown until data is collected from at least 3 seismograph stations. Circles are drawn around each station on a map, with the radius of the circle representing the distance the waves have traveled from the epicenter. The intersection of the three circles marks the epicenter of the earthquake. Experiment overview. The purpose of this activity is to locate the epicenter of an earthquake that occurred somewhere in the United States at 5:48 a.m. The time delay between the arrivals of the P and S waves at various seismograph stations around the country will be calculated, and the distance from the epicenter will be determined for each station. Pre-lab questions. You're going to go ahead and answer these with me. The space for us to do that is here on the next page. Compare and contrast primary and secondary waves. So we want to think of some things that primary and secondary waves have in common, and also some things that make them different. So the first thing that I can think of that they have in common is that they are both body waves. So both are body waves. That means they both pass through Earth's interior. Some things that make them different, however, are P waves move in the same direction as the rocks move. And the S waves move at a right angle to the rocks. We saw that with the two slinky demonstrations that we did back when we were in class. Another difference that I can think of between those two is the speed that they move. P waves are faster and arrive first. S waves are slower and arrive second. And there's one more difference that I can think of. S waves can't pass through liquids. All right, let's go back to question 2. Remember, you can always pause the video at any time if you need some time to catch up. Number 2, why must data be obtained from at least 3 seismograph stations to locate the epicenter of an earthquake? Hint, draw 2 intersecting circles, like a Venn diagram, to see how many points of intersection are formed. We actually answered this in our notes the other day. If we draw 2 intersecting circles, and I'm going to make them different sizes because the earthquake would have traveled different distances to different stations. So here's one, here's the other. How many points of intersection do we get? We get 2. There's one here and there's one here. So with 2 circles, you get 2 possible points. But if you draw 3 circles, that one's not a very good circle. And then with the third, I always cheat a little bit because I know where it needs to go. So there's our 3 circles. Okay, then you can see that there's only 1 point where they all intersect. So 1 possible point. And when they were actually doing this in real life, you would have data for more than 3 stations. And in fact, when we do the actual lab activity, we're going to have data from, I think, 4 stations, maybe 5 stations. But you actually only have to have 3. 3 is the minimum. You can have more than that, of course, and that kind of backs up your data and reinforces your data. But 3 is the minimum that you have to have. All right, question 3. Vibrations from a primary wave were detected on a seismograph at 2:04 and 54 seconds p.m. The secondary wave arrived at 2:09 and 13 seconds p.m. Determine how much time in seconds elapsed between the arrivals of the two waves. There's more than one way to do this, so if you have a method that works for you, that's fine. I'm going to show you the method that works for me. So when I do this, I write down my two arrival times, 2:04:54 and 2:09:13. And then instead of trying to subtract, I start with the first time and I count up. So if I started with 2:04:54, how many seconds would I need to add to get to 2:05? Well, there's 60 seconds in a minute, so 60 minus 54 means 6 more seconds. So if I added 6 seconds, that would take me to 05 minutes. Okay, and then if I was at 2:05, so 2:05, how many minutes would I need to get to 2:09? 9 minus 5 is 4, so there's 4 minutes in between. 4 minutes, and we're going to have to add these together eventually, so I'm going to put this in seconds. There's 60 seconds in a minute, so 4 minutes times 60 seconds each is equal to 240 seconds. And remember, that's the time that it takes me to get to 2:09. And then, if I'm at 2:09, how much more time do I need to get to 2:09:13? Well, I need 13 seconds. So 13 seconds, and that takes me to 9 minutes and 13 seconds. So then I look at what time I have, and I add all of them together. 6 seconds plus 240 seconds plus 13 seconds. So 6 and 240 and 13. And I add those all together, and I get 259 seconds. So the lag time, the seconds that elapsed between the arrivals of the two waves, was 259 seconds. All right, let's go back to the directions. So we're done with the pre-lab questions now. And again, I have all of these things here in case you don't have all of your materials. You can just follow along with me. Okay, directions. Calculating the time delay and the distance. Step 1. Using the data from the Find the Epicenter worksheet, calculate the difference in time between the arrival of the P wave and the S wave for each city. Record the time delay in seconds in the data table. All right, so let's find our data table here. Okay, we've got 5 stations. So eventually, since we're going to be drawing on the graph in color, I'm going to go ahead and color code these stations on my data table. And if you have yours with you and you want to play along with colors, that's fine. If you don't, that is okay as well. Okay, so I am going to make New York red. And Louisville is going to be green. Wisconsin is going to be blue. Pueblo is going to be orange. And Phoenix is going to be purple. All right, so the first thing that I'm doing is figuring out the time delay between the S and the P waves. So this is where you might want to have your scratched piece of paper like I do, but again, if you don't have that, you can just kind of follow along. So the first one we need to do is New York. So NY. And that is red. The P wave arrived at 5:52 and 40 seconds. And then the S wave arrived at 5:55 and 18 seconds. So, how much time is going to get me from 5:52:40 to 5:55:18? Okay, so the first thing that I need to do is get myself to the next whole minute. So how much time do I need to add to 40 seconds to get to minute 53? So 60 seconds in a minute, 60 minus 40, there's going to be 20 seconds to get to 5:53. Once I'm at 5:53, how many minutes do I need to get to 5:55? 55 minus 53 is 2 minutes. But I'm doing this all in seconds. So 2 times 60, that's 120. So 120 seconds. And then, now I'm at 5:53. How much more time do I need? 18 seconds. So 18 seconds. And I total those all up. 20 plus 120 is 140. 140 plus 18 is 158 seconds. So that is my lag time. So then I'm going to go back to my data table and fill in the time delay, and maybe I'll just do this in the color, is 158 seconds. That's the lag time between the S wave and the P wave. All right, let's do the next one. So Louisville is in Kentucky, and that one is green. Let's write out a little bit more work for this one, just in case you guys need to see it. So the P wave arrived at 5:49 and 20 seconds, and the S wave arrived at 5:50 and 11 seconds. So we have how many more seconds to get to the next whole minute? So I'm at 20 seconds. The next whole minute would be at 60 seconds. So 60 minus 20 is 40 seconds. If I add 40 seconds, that's going to take me to 5:50. And then 5:50 to 5:50, I'm already there. So how much more time do I need to add? 11 seconds. So 40 seconds plus 11 seconds is equal to 51 seconds. Okay, so then I'm going to go back to my data table, and the lag time for Kentucky is 51 seconds. Okay, Green Bay is next. So the next one is Wisconsin, and Wisconsin is blue. The arrival time for the P wave for Wisconsin is 5:50 and 20 seconds, and the S wave is 5:54 and 21 seconds. So, oh, whoops, I looked at the wrong line. 5:51. Make sure I get that right this time. 5:51 and 52 seconds. 5:50, 20, 5:51, 52. Okay, so how much time passed between these two? So I'm starting at 20 seconds. I'm going to need 40 more seconds to take me up to the next whole minute. So 40 seconds is going to get me to 5:51. And then, again, I'm already there. I'm on the same minute as the next arrival time. So I just need to add 52 more seconds. So 40 plus 52 is 92 seconds. So go back to the data table and we're going to fill in 92 seconds for Wisconsin. Two more. Pueblo, Colorado. Okay, Colorado is next. Colorado is orange. The arrival time for the P wave is 5:52 exactly. The arrival time for the S wave is 5:54 and 21 seconds. So how much time is in between there? Okay, well, we're right on the nose with the 00 seconds. So I just need to start with the minute question. So how many minutes are going to get me from 2 to 4? So I need 2 more minutes. So 2 more minutes times 60 seconds each is 120 seconds. And then that puts me at 5:54. So how much more time do I need? 21 seconds. So plus 21 seconds gives me my lag time for Colorado, which is 141 seconds. So go back to the data table, 141 seconds. One more. Phoenix is next. So this is Arizona. Arizona is purple. And my arrival times for Arizona were 5:54 and 40 seconds and 5:58 on the nose. So how much time passed in between? Again, I count up. So 40 seconds, I'm going to need 20 more seconds to get to the next whole minute. So 20 seconds is going to get me to 5:55. And then how many minutes are between 55 and 58? That's 3. So plus 3 times 60, so that's 180 seconds. So 20 plus 180 is 200 seconds. So then go back to my data table and fill in 200 seconds. Okay, let's go ahead and stop this first video here, and that will be all for today. And then tomorrow we will do the second half of the lab.